All right. So guys, we are recording this. We did all of the equilibrium lectures in this block. So this is really a lecture that, or it's not even a lecture, it's like 30 minutes of helping you get ready for problem set 15. I think we're recording this because F block will not have a chance to get this because they're getting lectured at for the next couple days. So a big part of the equilibrium, yeah, that happened. A big part of equilibrium are what we call Rice charts. So Rice charts. So the question is, where do we take these notes? You have a sheet that says the tail of really big K and really little k. So in order to solve these equilibrium problems, to figure out our concentrations at the end of a reaction when we've reached equilibrium, we need to use what's called Rice charts and K values. So the problem with these Rice charts is that they oftentimes can involve quadratics. And quadratics are generally not particularly enjoyable to do. So let's go through and we'll do number one. So number one, it says when water is present in a solution of formaldehyde, the equilibrium shown below is established. So note that it says D. So you can have water dissolved in something else, and so you could have the concentration of water in something else. So we have the K value, and we have initial concentration. So we start with this. All right, Griffin, what's our color? What is it? Yeah, no. All right, what's the next color? Green. I think that's a green. All right. So we have CH2O plus H2O. I'm not doing lust, the color. All right. Yeah, I already did read that. Okay. So here's our reaction. So what does the I in Rice stand for? You're thinking kinetics. It's not intermediate. Initial. So and it gives us our initial concentrations of both formaldehyde and water. Is it 0.5? What's my, and I like to draw the line between products and reactants. What's my initial concentration of formalin? Before the reaction starts, what's my concentration of formalin? 0. All right. So all of a sudden I start the reaction, gets going. What happens to my concentration of formaldehyde and water? It goes down. What's my mole ratio between these two? 1 to 1. 1 to 1. All right. So I don't know how much goes away, but I know it's the same amount of both. So I just subtract X. And if I lose X amount of formaldehyde and X amount of water, how much formalin do I get? Blank for F. Daniel. If I lose X amount of these two things, how much of this do I gain? What's my ratio between this and this? 1 to 1, right? So if I lose X of this, how much of this do I make? X. So I'm adding X. I'm losing a certain amount of my reactants, and I'm making that much product because of the mole ratio. So the reaction happens, the reaction happens, the reaction happens, and then I don't know what happened there. I reach equilibrium. So at equilibrium, I have 0.5 minus X here, 0.32 minus X here, and X of my formalin. This is a 5. Sorry. It says it in the... Yeah, Elizabeth. Right here. So the question was, how did I get the 0 here? So we're assuming that before the reaction starts, I don't have any product. So that's the assumption we make right there. And so that's why it's 0. Okay. Now, what's the next color, Griffin? Smitten. Yeah, I'm going to go with pink. Okay. So, what is my expression for K? Let's see if we can go back to chapter 15. See if we remember, how do we set up an expression for K? You're going to be doing this a bunch. Products over reactants. So it's my concentration of formalin over my concentration of formaldehyde and water. Now, what would have been different if I had had a coefficient in front of the formaldehyde? What would change then, Johanna, if I say this was 2 instead? How would my equilibrium expression change? It wouldn't double. Oh, interesting thought. But we would actually change this whole expression. Well, not whole. We would change one part of this expression. Whenever I have a coefficient here, think of rate laws. So if you have a coefficient in your elementary step of a rate law, where does it go? Yeah, same thing for equilibrium. So if I had 2 CH2Os, I would put an exponent here. But since they're all 1 in this case, it's just 1, 1, and 1. All right. I'm choosing this time. So now I have my K expression and my K value. My K value was 75.5. So I know 75.5 equals my formalin concentration over my formaldehyde times water at equilibrium. Well, I have all of these values. Well, not quite. I have an expression for all of these. So what's my numerator? What do I put in for my numerator? Cameron. What do I... So we're at equilibrium, right? Here. So what do I put in for my concentration of this at equilibrium? Nope. So just X. So my concentration of CH2O would be what? All right. Now, nice and easy. Let's solve for X. All right. So I'm going to give you guys a couple minutes to do the algebra required. You're probably going to need a calculator to do this. Let's see what you guys get when you solve for X. And see if it matches what I got. Oh, like the brackets? No, yeah, you get rid of it. All right, so you should all have this down. I'm going to leave it on a blank page and copy that over again. All right. So here's as far as I would expect you to go. Check to make sure you got this as your quadratic that you wanted to set up. Now, I would totally give this to you as a multiple choice question on a test. Solve for x. Have to use the quadratic equation. What is it? Negative b plus or minus the square root of b squared minus 4ac all over 2a. All right. Easy. Nice and easy, right? So now, here's the thing. You plug this into the most common mistake people make with this. And generally, let me just say this. We're never going to give you a quadratic on a test. This just, what's the point? It's just too much time to prove to me that you can do algebra. Like, it doesn't show that you have the understanding, right? So I'm not going to have you do a quadratic on a test. But you should get 2 answers for this. So, Edward, what were the 2 answers you got? Do people agree with Edward? I also agree with Edward. Okay? Now, one of these does not make any sense. Which one of these does not make any sense? Why the 0.533? Yeah, this cannot happen. You would end up with a negative concentration of water. You cannot have a negative concentration of water, right? So it said calculate the concentration of formalin in the solution at equilibrium. Here is your answer. Now, here's why this makes sense. K is bigger than 1. So what would you expect that you have more of, products or reactants? Let's go back to... So at the end, would you expect to have, if K is greater than 1, would you expect more products or more reactants? More products, right? You expect your numerator to be bigger than your denominator. So you would expect the reaction to proceed forward, and you get a bunch of products. This is what we call a normal size K. This is neither really large nor really small. The next problem involves a really tiny K. So we have a reaction below that is, the K is 3.71 times 10 to the minus 18. That's what we call a tiny K. So in this reaction, what do we know? Is it going to favor the products or the reactants, Alexei? Reactants, right? This reaction will not move forward very much. Almost none of it will move forward because K equals the concentration of products over reactants. So if K is tiny, that means we have almost no product. This is going to be very helpful for us. So, Griffin, next caller. Thistle, that's like a brown. Which I don't, where's the, all right. All right, so we have rice. We have a different equation, but you'll see something nice in a second. Whoops. So similar organic reaction with water, and instead we make this. All right. Well, what is our initial concentration of C3H6O, which I can't say the name for because it could be multiple different things. Yeah, Wesley. 0.5. And water, 0.32. And how about this, our product? 0. All right. So the reaction happens. I use up some of my product, so negative X, negative X. Griffin, what should I put here? I used up some of my reactants, plus X. Okay. So now I'm left with the exact same equilibrium expression that I had before. Except now, instead of it equaling 75.5, I have 3.71 times 10 to the minus 18th equals X over 0.5 minus X times 0.32 minus X. Okay, chemists, what do you think I'm going to ask you to do? Solve for X. Solve for X. Sorry, I'll leave that up for a second. And the oh, what are you? All right. So I'll be honest that the computer program I used to solve this wouldn't let me do it. No. Is anybody getting numbers? Let's see what we're getting for numbers. All right, well, what'd you get? Yeah, that's not it. Ten to the 17th. Yep. And 0. So, do you think this could at all be? Did you get 2 numbers? And what'd you get for x? Oh yeah. So, yeah, my calculator or the computer program I used also gave me that as an option and 0 as the other option. So what does that mean? If by this quadratic equation x is giving us 0 on every single calculator and computer program, what does that mean about the size of x? It's not actually 0, but what do you think? It's really teeny, 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 tiny. All right, so let's go back. So actually I'm going to move this. And I'm going to rewrite my rice chart and make it a lot easier for us. All right, Griffin, next caller. Flocks. All right. Okay, so we have a really small k now. So that means our x is going to be teeny tiny. It's all right. So my initial is, like we said, and some of this is still reacting, right? So I'm losing x and gaining x. But now, if x is really small, 0.5 minus something times 10 to the negative 18th, what can we consider that to be? So this is the Bill Gates analogy. Bill Gates is still the richest man in the world. If Bill Gates was walking down the street and picked up $5, would that change the amount of wealth that he has? Really? No, instead of having $3 billion, it's not like he would have necessarily $3 billion and $5, right? You know, because we don't know exactly what the numbers are after $3 billion. But would that really change how much money he has? No, not by a lot. Also, similarly to Sophia, about how far is your house from here? 3 miles. How far is it from here? How far is it from here? How far is it from here? Still 3 miles, right? So even though I'm moving a little bit closer or further away or parallel or whatever, it's not really changing how far away your house is by an amount that matters. So if you have a very small k, you can ignore the amount of x that gets reacted. Now, if Mr. Bennett's walking down the street and finds $5, I'm going to pick it up because that's going to change the amount of wealth that I have, right? So it matters to the person who started with 0, okay? So I leave this as x. It doesn't matter to Bill Gates or Elon Musk or any of these like really rich people, but it matters to someone who doesn't have a lot of money, okay? So now I can rewrite my equilibrium expression. Fingers crossed. Okay. Do people need me to wait here for a second? I can rewrite my equilibrium expression like this now. Oops. I can do it this way. Now, can somebody please solve for x for me? Sounds about right to me. Okay, so that is my concentration of C3H8O2. I had a really small K. Isn't that a lot easier than doing a quadratic? Yes, that you will get on a test. You won't get medium-sized Ks on a test. You will get small Ks. And now we have to tell, so that's the story of really tiny K. Yep. The reason you can do that is because it's negligible. Yes. Yeah. Yeah, Johanna. So you should be able, there's like rules on like the following pages that tell you what's big K and what's little k. It's really like 4 orders of magnitude. So like 10 to the minus 4 is really small, 10 to the 4th is really big, anything in between is in the middle. If we did give you a medium-sized K on a test, it wouldn't be with an eye towards doing a Rice chart. You'd have it for another reason. Okay. All right, let's do the really big K. All right, number 3. So K is 1.24 times 10 to the 24th. Here's my reaction. So now I have a much more reactive substance. So big K means my products are very much favored by this reaction. If I start with this, the reaction is going to go almost all the way to the products. So don't expect all of your initial concentrations to be 0.5 and 0.32. Just, all right. Because I want to give you some time to work on problem set 15, I will give you a hint. So, really big K. What am I assuming is going to happen to this reaction if my K is really big? You're going to get, essentially you're going to get all the product. Okay. Here's where this changes. So this, we're going to say this is traditional. With really big K, we need to change our Rice chart. We need to make it a Rice chart. All right. Like a spaghetti chart. All right. Oh, I need to add another slide. It's Rice for a reason that you will now see. Okay. Whoops. I did not want to do that. All right. So R. So we have the same setup up front. All right. Same setup up front. Same I. Different C. It's C. Actually, no. Wait. Same C. Different C here. So it's Rice. It's all the same until the 3 C's. Now, so initial, let's just walk through. Let's fill it in. What's our initial concentration? Well, it's still 0.5 and 0.32 and 0. Here's where the Rice chart gets a little trickier. You're assuming that this is changing. Well, you're going to figure out exactly how much it's changing. If this reaction goes to completion, how much of the, so this goes back to stoichiometry. If this reaction goes to completion, how much of each of these things am I going to make? Or am I going to use, sorry. Let's see. Trevor. So it's my ratio is 1 to 1 to 1, right? So if I have 0.5 of this and 0.32 of this, let's just start with how much of this can I make? Yeah. So I'm going to add 0.32 here, minus 0.32 here, and minus 0.32 there. So the question was, will that give us a 0 in the denominator? Yes and no. Well, I'll show you why it's no. Okay, so this C, this second C, we'll do C1, C2, and C3. C2 is when the reaction is said to go to completion. So when this reaction has gone all the way forward, I have 0.18, 0, and 0.32. So this is assuming the reaction went all the way to the end. I used up all my limiting reactant. But this is equilibrium. So that means I don't just go in one direction. C3 is change back. So we're doing a little mathematical gymnastics with this. We're assuming the reaction goes all the way forward. And then once it's all the way forward, let's assume it goes back just a little bit. So we know our equilibrium. So now my reaction's moving backwards. I subtract x from here. What do I add here? Now, because I have a really big K, I know that that reaction is not going to go backwards very much at all. It wants to stay mostly as the products. 0.32 minus the teeny tiny number is 0.32. 0 plus x is 0.18 plus the teeny tiny number is 0.18. So now I finally can use, oh, I didn't want to erase that whole line, but whoops. I finally can use my K value. So 1.24 times 10 to the 24th equals 0.32 over 0.18x. So solve for x. What do you got, Griffin? Yep. Do people agree? All right. That is our answer for our concentration of water at equilibrium. So now you guys know how to solve problems with normal K, which you would probably only see on the problem set, big K and little k, both of which you could see on tests, because they will not involve using quadratic functions. So now you guys have 25 minutes to work on problem set 15, or talk to each other. I don't have the computers for the lab, but you work on what you need to.